Okay, welcome to your next video in topic 2.1 of motion. And what we're going to do is we're going to, in this video, I'm going to derive what are called the equations of motion for things moving in a straight line with a constant acceleration. Okay, so this is a really important one because you're going to be using these equations off and on for the next 2 years in this class. Okay, so the first thing I want to do is I want to talk about how things. I just want to remind you of how things fall near the Earth's surface and this concept of free fall, which we've gone over before in previous videos. Okay, remember that near the surface of the Earth, the acceleration due to gravity, which is called g, little g, is 9.81 meters per second squared about, and it's negative because it's always acting downwards towards the center of the Earth. And we talked about how g varies at various locations around the Earth. So generally, the farther you are away from the center of the Earth, the lower the value of g, but not always, because it depends on things like the density of the Earth between you and the center and what the Earth is made of and so forth. But generally, we take 9.81 meters per second squared to be g. Now, remember from Newton's second law, F equals ma, that we came up with the equation W equals mg, which is weight. And obviously, I just want to point out, an object doesn't need to be accelerating or moving at all in order to have the force weight acting upon it. There's always a weight to every object near the surface of the Earth, okay? And then we saw this kind of funny video of the guy dropping the champagne bottle off the top of the building. And we defined free fall being the conditions where an object is only under the influence of gravity. An object can be moving up or down and be in free fall. So it's important that you recall those key concepts. Okay. All right. Okay. Now, free fall is an example of uniformly accelerated motion in a straight line. Okay. So that's why we really use. It's a really good introduction to the equations of motion, which deal with only acceleration in a straight line. Okay. We'll deal with acceleration not in a straight line when we deal with circular motion, but for now we're going to keep it fairly simple. When we talk about motion, we sometimes use what are called motion diagrams. And what this is basically the vector sum of VF and negative VI always give you a change in V, okay, change in velocity. And it turns out that, remember, the change in velocity, the direction of that change in velocity vector always points in the same direction as your acceleration. So in this case, these are, you can almost think about this as like dots, like ticker tape dots, like we talked about before. The dots simulate the position of a spacecraft as it's landing on Mars, and clearly it's slowing down because the dots are getting closer together. Okay, so for each particular segment, if you do your delta change in velocity equals your final velocity minus your initial velocity, well, that's the same as your final velocity plus the negative of the initial velocity. You always get that your change in velocity vector is pointed upwards, and in fact, the acceleration of the spacecraft is upwards at every single point in time. That's what slows it down so that it has a nice landing on the surface of Mars instead of crash landing at a high speed. Okay? We can also deal with motion diagrams for parabolic or projectile motion, which I'll talk about a little bit more in the next couple of videos. Okay? If you do your VF minus your VI, you get a delta V. Okay? So really cool. Again, delta V, the change in velocity vector, always points in the same direction as your acceleration vector. Even in this case, with uniformly accelerated motion, this is uniformly accelerated motion in a straight line because even an object being thrown horizontally or at an angle, it's always accelerating downwards at 9.81 meters per second squared. Okay? Note that in each case, delta V is VF minus VI, which always points in the same direction as A. Okay? Okay, so go ahead and do this example on your own. You might want to bring up LoggerPro and do this. If you want to do it by hand, you can, but I find it simpler with LoggerPro. So pause the video and give this question a shot. Okay, you have a cannonball initially at a height of 1 meter on the edge of a high cliff. Is shot directly upwards with an initial velocity of 25 meters per second squared. Fill in the following table and graph the data. From your graph, what's the acceleration? Okay, well, these are the values that I got for V, okay? And the graph of velocity against time is, of course, a straight line with a negative slope, and that slope is exactly equal to the acceleration of the cannonball because the slope of a velocity time graph always gives you acceleration. So in this case, LoggerPro told me, this is pretty cool, this is real data, negative 9.813 meters per second squared, okay? All right. Notice that the fact that the cannonball was initially at a height of 1 meter is irrelevant in this problem. Okay. Okay, now what I'm going to do is I'm going to actually derive for you the equations of motion. Okay, for something moving, it could be anything moving at a constant acceleration in a straight line. Okay, so I want you to consider the following motion graph. This is the velocity time graph, where the velocity of the object is not zero. It starts off at 20 meters per second, and it accelerates at a uniform rate between 20 meters per second and 40 meters per second from the point P to the point Q. Okay? All right. So that's, just so you know, that's what we're dealing with when we deal with this, the derivation of the equations of motion. We're going to deal with the same graph over and over. Okay? Now, you know that the slope of the graph gives you the acceleration of the object. I'm going to let U be the velocity at P, the initial velocity. Remember, we always call that U in IB physics. V will be the final velocity, or the velocity at Q up here. Okay? Since the slope is the acceleration, the slope is clearly the final velocity minus the initial velocity over delta t, or I'm going to call it v minus u over t. Okay? Or, in the most simplest sense, v equals u plus at. This is the first equation of motion, and it seems really easy. Keep in mind that these four equations of motion that I'm going to derive for you are actually given to you in the data booklet. Okay? So there's no need for you to memorize them, but you should be comfortable with deriving them. This one is really easy, really simple. Okay? So that's the first one. Okay. For the second one, we're going to note that the area under the graph is the area, is the displacement of the object, okay, from 0 to 5 seconds. And this area, which has height u, okay, this area consists of a rectangle and a trapezoid. The rectangle has a height of u, which is 20 meters per second, and a length of t, which is 5 seconds, okay? And the height and the area up here of the rectangle is just half of this triangle. Or if you memorize the equation for a trapezoid, you can deal with that too. Okay? So in effect, the area is the object's displacement, which becomes u times t. Okay? This u times t is the rectangle down here. Okay? 1/2 v minus u times t is the area of this triangle right here. Okay? Now, again, the equation that we got before, v equals u plus at, if we substitute in at for v minus u from 1, what we get is s equals ut plus 1/2 at squared. Okay? So, kind of interesting. That's our second equation of motion. Okay? So, if you don't get that algebra, you might want to rewind it. Do the substitution yourself. You should be following along on a sheet of paper with these equations, making sure that you follow and understand and get and agree with the algebra. Okay? All right. So for the next equation, I'm going to notice something about the object's average velocity. I can think about the average velocity. I can calculate it from its displacement in time. And you can also calculate the object's displacement from its average velocity. So for example, the average velocity is just going to be v plus u over 2, right? Okay. In this case, it's going to be 30 meters per second because 30 is right in the middle of this uniform motion here. Okay, and that's the change in displacement over the change in time. Okay. Turns out that if I solve this for delta s, or the displacement, I get v plus u over 2 times t. I just multiply both sides by t. That's my third equation of motion. Okay, which comes from the average velocity. Okay. Okay, make sure that you get that. Okay, so far we have these four equations, okay, or these three equations, okay? V equals u plus at, s equals ut plus 1/2 at squared, s equals v plus u times t over 2. That's 3, okay? And what I'm going to do to get the fourth one is I'm going to express number 1 as, I'm just going to rearrange it and solve for t, and I'm going to substitute this expression for t into the third equation. Okay, here's my v minus u over a right here, giving 2as equals v plus u quantity times v minus u, or in other words, v squared equals u squared plus 2as. That's number 4. These are my 4 equations of motion. I will be using them all the time for the next 2 years in this class, every time I have a situation where an object is moving at a constant acceleration in a straight line. Super important that you understand these. Like I said, you don't necessarily have to derive them from scratch, but you really need to understand deeply where they come from and have a real intimate knowledge of where they come from. Okay, and I derive them for you graphically. There's a way to derive them using calculus, of course, and maybe we'll talk about that in class if you wish. But for now, these are the 4 equations of motion. They'll be given to you in your data booklet. Okay, now we're going to use these 4 equations of motion over and over and over again to solve motion problems, where I give you a couple of parameters and I ask you to ask you to find something else or how something else changes. Okay, so what we're going to do is the following. We're going to make what are called SUVAT tables. I'll show you what I mean by that. Okay, you're going to fill it in based on what you're given, from that, you can easily identify which of the 4 equations you can use based on what you know, and then solve it and check your answers if you have time. One of the things to really keep in mind is that there's almost always more than one way to solve these kinematics problems. Sometimes there's as many as 3 ways, sometimes 4 ways, depending on how many steps you want to take. So let's get right into doing some examples, okay? And for each of these examples, I'm going to have the equations of motion up here at the top of the slide just so that you can refer to them as needed, okay? So your first example, go ahead and read it. Okay, mass has an initial velocity of 10 meters per second, moves with an acceleration of -2 meters per second squared. When will it have 0 velocity? So clearly, this object is moving in the positive direction with an initial velocity of 10 meters per second. If the acceleration is negative, eventually it will stop because it's constantly slowing down. Okay? Now, here's how we use the SUVAT process to do this. Here's my SUVAT table. Okay? S means displacement, U is initial velocity, V is final velocity, A is acceleration, T is the time. In this situation, I'm given the initial velocity, which is 10 meters per second. I'm given the final velocity, okay, which is 0 meters per second. Okay, the acceleration is -2 meters per second. Always include your negatives and positives. And I'm asked to find the time. Now, knowing the variables u, v, and a, and asked to find t, which of the above equations do you think that you would use to most easily solve this problem? Okay. Exactly, v equals u plus at, and when I solve that for t, I get 5 seconds. Okay. Notice how I kept my negatives in here. Keeping the negatives and positives, it's really important, or else your answer will be sometimes nonsense. For example, what if you got the top? What if you mixed up your negatives? You would have gotten -5 seconds, which obviously doesn't make sense, right? Okay, so you want to really keep your brain on in terms of what kind of answer makes sense and what kind of answer doesn't make sense. Occasionally, when we're doing kinematics problems using these equations, especially when we deal with a quadratic, we sometimes get 2 solutions for time, and always one of those solutions for time will be nonsensical or it doesn't make sense. More often than not, because it's negative, and negative time doesn't make any sense at all. Okay. How about this one? Example 3. What's the displacement after 10 seconds of a mass whose initial velocity is 2 meters per second and moves with an acceleration of 4 meters per second squared? Well, clearly it's speeding up. Here's my SUVAT table. I'm asked to find s. My initial velocity is 2. The acceleration is 4. Time is 10. For this one, you would use probably the most simply ut plus 1/2 at squared. You should explore and see if you can use another set of motion kinematics equations to do this one. Maybe you can. I got positive 220 meters for my displacement in this one.